So, starting on the 3.1 notes, or 3.10, sorry, notes, we're working with trig equations and inequalities. The first half is equations, the last half is inequalities. And starting off, one thing that's helpful to have is a unit circle handy. I've got mine pasted here. You might go back and rewrite this unit circle to have it handy, and pause the video, come back. And another thing that's going to be helpful is to start, it says consider the following two equation statements: sine of x equals 1/2, and then the inverse of that, right? Like right here, my sine is on x, and here my arc sine is on the 1/2. So you might be tempted to think that these two equations are equivalent. The answer is no. And really, instead of no, it'd be not quite. Because remember, the domain of sine is not restricted. The domain of sine is not restrictions. But for the domain restrictions of arc sine, if you go back to 3.9, you can remember it can only work with the right half of the circle. The domain is restricted to the right half of the circle. So, because of that, this function will only output answers over on this right side of the circle. And that's exactly why when we're working with this, whereas this equation 1 has two answers right here. So when is sine of x equal to 1/2? That happens at 5 pi over 6 and pi over 6. But when I input 1/2 into arc sine, it's only going to output pi over 6. Because remember, arc sine only works with this half of the circle. So knowing these, that's why I started this on 3.9. This is super important to remember. And as we work with this to find a general solution, since trigonometric functions are periodic, that means they repeat, we can have infinitely many solutions to an equation if no domain restrictions is given. So in our equation above, we're going to consider that. It says sine of x is equal to 1/2 when I have x equals pi over 6 and x equals 5 pi over 6. But because sine is periodic with a period of 2 pi, like pi over 6 can end up at 13 pi over 6. Like inputting pi over 6 and 13 pi over 6 outputs 1/2, and so does 17 pi over 6. So we could rotate around the unit circles as many times as we wanted and create infinitely many angles. So remember, for sine and cosine, the period is 2 pi. And for tangent, the period of the parent function is pi. And so for example, and this is just an example. So if I'm finding the solutions, the general solutions for sine of x equals 1/2, I would go up to my unit circle. So for answer, like steps here, I would find answers on my unit circle. And then the second thing that I would do is write plus my period times k. Like that's how you write it. So x equals my answers on the unit circle plus my period times k. Because what this is saying, so in this box here, that's saying my period is 2 pi times k, and I think of k as the number of times I move by the period. So in this example here, let's look at it right here. The example that I just highlighted here, this is saying I start at pi over 6 and move by 1 period. So my k value here is 1. If I wanted to move by 2 periods, I would have 2 pi times 2, and that would move me 2 periods. Because all of those output the same answer. Same thing with cosine. The only thing that's different is because the period of tangent is pi, one equation will capture all solutions. So for example, when is tangent of x equal to 1? Well, tangent of x will be 1 here, here, oh, not 1 here, here, because remember, tangent is positive, negative, positive, negative, because right here it's y, tangent is y over x, so this would be negative over negative, which would give me a positive. So tangent is equal to 1 at pi over 4 and 5 pi over 4. Okay, and the only difference to get from here to here is add pi, and to get back to there, I would add another pi. So that's why tangent here, you can just write it as the single 1, because pi will take you halfway around the circle to the matching counterpart. So let's do some examples. So find all solutions to the equation cosine of x equals negative square root of 2 over 2. So I go to my unit circle here. Let me paste that in here. I'm going to cut my unit circle here. And I'm looking where it is negative square root of 2 over 2. Remember, cosine is the x value. So I'm going to go through, that's here and here. So the way I write that, my two solutions, or my two general forms of solutions, because technically there are infinitely many, I'm going to have x equals whatever that value is, so 3 pi over 4, plus the period of cosine is 2 pi, so 2 pi, okay? And you don't have to say where k is an integer. On the AP exam and on my exam, it's it'll be just common knowledge that k means an integer. So same thing here. My other answer is at 5 pi over 4 plus 2 pi k, because that's going to repeat all the way around the circle. Now sine of x equals negative 1. That happens, remember, negative 1 as the y-coordinate, because sine is y. So my y-coordinates, the numerical versions of the y-coordinates happen here. And the only one that is negative 1 is at 3 pi over 2. My period is 2 pi on sine, so plus 2 pi k. That's why it's just 3 pi over 2 here. There's not, this is just positive 1, this is 0, and this is 0. There's no other place where sine is equal to negative 1. And then here, you're looking for find all solutions to the equation where tan is equal to 1 over the square root of 3. And when you're doing tan, what I would say is find the smallest theta where this happens. Okay, find the smallest theta where this happens, because remember, if I go back to my note here, I only have to write one equation because the period is pi. It's going to capture both. So remember, really what this looks like is 1 over, like when you see 1 over square root of 3, this is saying 1/2 over these, because the 2's will cancel out. So I'm looking for 1/2 over the square root of 3 over 2, and that happens right here. That happens right here. So I can say x equals pi over 6. And remember, the period is, that's the main difference between these. The period was 2 pi for these, but in this, it's just pi for tangent, pi k. Because remember, why do I not have to write 7 pi over 6? Because negative 1/2 divided by negative square root of 3 gives me this answer, right? Well, if I add pi and go halfway around my circle, I end up at 7 pi over 6. So this one answer takes care of both. And when I'm solving trig equations, it's very similar to this. So I'll paste another unit circle right here. There's not going to be, oh. Paste, boom. There we go. So isolate the trigonometric function on one side of the equation. So get your trig function by itself. And then Find the corresponding angle measure on the unit circle. Consider any domain restrictions. So remember, this is going to happen, like for the domain restrictions, this is mainly going to happen when they tell you, like for example, on number 5, what are the x coordinates of the points of the intersection of the graph of f and g for 0, like theta is between 0 and 2 pi. So this is an example of a domain restriction. This is an example of the domain restriction. Because look at what this says. This is a domain restriction, whereas this says what are all values of theta. So if your domain restricted, you don't need like what that means is on where we wrote the general solution, because this is saying find all solutions, I wrote plus 2 pi k for sine and cosine, and on example 3 it says find all solutions, so that's why I wrote plus pi k. But on example 5, for example, it just wants the solutions that are basically all the pi values that are on the unit circle, so I only need to write that. I don't need the plus pi k. Let's see what I mean. So what are all the values of theta where this is true? So let's write that out. This looks worse than what it really is. So my first step is to isolate this. So I'm going to say 6 divided by 6, have sine theta equals 3 over 6 simplifies to 1/2. So I'll have square root of 2 over 2. And now I'm going to look on my unit circle for what theta values give me pi over 2. I mean, not pi over 2, square root of 2 over 2. So I'm going to say theta equals, let's find the first one. Square root of 2 over 2 happens at pi over 4. So pi over 4 is one of the answers. And then because it says all solutions, or all values, that's when I add the period. So plus 2 pi times k, comma. So now the other solution, it is at 3 pi over 4. Because that's when it is square root of 2 over 2. So 3 pi over 4 plus 2 pi k. And that's done. So my theta values here are pi over 4 plus the period of sine, and 3 pi over 4 plus or minus the period of sine. Any number of periods. So remember, k is just how many times you want to do the period. And on 5, let f of x equal this and g of x equal 2. It says, what are the coordinates of the intersection? The x coordinates of the intersection. They intersect when they're equal. So set them equal to each other. 3 plus 2 cosine x equals 2. That's minus 3, minus 3. You solve this like a normal equation. So 2 cosine x equals negative 1. Divide by 2, divide by 2. You get cosine of x is negative 1/2. So what x values here give me negative 1/2 for cosine? Remember, cosine is the x values. So, and I want negative 1/2, correct? Yes, negative 1/2. So negative 1/2 happens at, I'll circle it in red, 2 pi over 3 and 4 pi over 3. But notice, the important thing is, I'm just going to write that. X is equal to 2 pi over 3 and 4 pi over 3. Because of this domain restriction here, I only need values between 0 and 2 pi. I don't need to add or subtract 2 pi. I don't want anything before 0, and I don't want anything after 2 pi. So these are my solutions that I need here. Okay? That's the main difference. So look for domain restrictions. Now, when we want to square trigonometric functions or raise them in any exponent, we don't want our notation to be overly complicated. If we wanted to square the expression sine x, we must be careful to write that. So what this is saying, this is the key thing to take away from here. This is the key thing to take away from here. If we have this, it's looking like, usually if you have sine of x, like the whole thing squared, you write it as sine squared of x. Because this just shows you that the squaring goes with sine. The squaring goes with sine. Okay, so for example 6, when I look at this, it wants to know the zeros of g. That just means zeros happen with set your function. You set your function equal to 0 and solve. You set your function equal to 0 and solve. And notice it's just on this interval in my domain restriction to the unit circle. Okay, so let's do that. So 3 minus 4 sine squared x. And the nice thing is this works very similarly to what you would think it would do. So I subtract 3. That gives me negative 4 sine squared x equals negative 3 divided by negative 4. I have sine squared x equals 3/4. And then I'm going to take the square root of this. And when you do a square root of a fraction, that's saying the same thing as the square root of 3 over the square root of 4. You can take the square root of the numerator and denominator separately. So sine of x is equal to, don't forget, plus or minus, because it needs to be the plus or minus values, right? It needs to be our plus or minus values. So when I take the square root of that, I get plus or minus. The square root of 3 does not simplify on top. And the square root of 4 is 2. So I'm looking for all the places where sine of x is equal to either positive, so either positive square root of 3 over 2, or negative square root of 3 over 2. And if it'll paste for me. Nope, it's not going to work. There we go. If I can paste this right here, zoom it out a little bit. There we go. I'm looking for all the places where it's square root of 3 over 2. And remember, sine is y, so I'm looking at pi over 3. It's all the pi over 3s, because I'm wanting positive or negatives. And what you'll notice in a lot of these where you have to work with squared, it's going to have the same denominator the whole time. And because it's in the domain restriction here, I don't have to write out the crazy version. All I have to do, I don't have to do the plus 2 pi k. I just have to write x equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay. Same thing here. What are the values of theta for the given domain restriction? Remember, this is always the domain restriction where cosine squared theta equals negative cosine theta. So let's write that. And what you're going to see when you're solving these equations, you're going to try to do factoring a lot of times. So if you see, like you see how there's a cosine and a cosine, don't be tempted to just divide here. That's going to jack you up a little bit. Let's add this over instead. Okay, you're going to have cos squared of theta. And because this is squared and this is not, I'm just going to add those like this. because they cancel out. And now I can factor out a cosine from each one of these. So I have cosine theta equals cosine theta plus 1 equals 0. I just factored out a cosine from each one of those. And the values for which this is going to happen, I'm going to set two cases, like this part equal to 0 and solve. So it's saying what's the x value when what point on here is my cosine value equal to 0? That happen. My x values are 0 at pi over 2 and 3 pi over 2. Pi over 2 and 3 pi over 2. So this gives me theta equals pi over 2 and 3 pi over 2. And then this one in blue, I take the parentheses and set it equal to 0 and solve. Cosine theta plus 1 equals 0. Subtract 1 on both sides. Cosine of theta equals negative 1. And when is cosine of theta equal to negative 1? That happens right here at pi, because the x-coordinate of pi is negative 1. So that gives me pi on this one. Theta equals pi. So if I was going to write a full list here in purple combining these, I'd say x equals pi over 2 pi 3 pi over 2. It doesn't matter that they're in order. I just like to write them in order. Last one. Example 8. When do they intersect? So intersect means set them equal to each other. So 2 sine squared x equals square root of 3 sine x. First thing to do, if you have them on different sides, so anytime you have, like, this is a good note to write, if you have trig functions on different sides, consider moving all to one side. Like, not always the case, but usually for this lesson at least, you're going to try to move it to one side. So what do I mean by that? I'm going to subtract the square root of 3 sine x. Subtract the square root of 3 sine x. And that gives me 2 sine. And this looks a lot worse than what it is. All I did was move that over. 2 sine squared x minus the square root of 3 sine x equals 0. And now I can factor out a sine from both of these. And that gives me sine x, parenthesis 2 sine x minus the square root of 3. So remember, you set both of these equal to 0. Sine x equals 0. So that one's asking, when is my y value equal to 0? My y value is 0 at 0 and pi. So that gives me x is 0 and pi. And then this one over here, I just go 2 sine x minus the square root of 3 equals 0. Add the square root of 3. Boom. Divide by 2. And I get this. When is sine of x equal to positive square root of 3 over 2? Notice I did not do plus or minus there because I did not take the square root. You only do plus or minus when you take the square root. So I'm looking for positive square root of 3 over 2. I'm just going to circle that. Boom. And that's pi over 3 and 2 pi over 3. So x equals pi over 3, 2 pi over 3. So if you want to connect it to one big answer, it doesn't really matter the order. If you wanted to just say 0 pi over 3, it doesn't have to be in order. Like, that's my full answer. starting on part 2 of this video, we solved inequalities of polynomials and rational functions, and we can also do the same using trig functions. So the first part here, we have the graph of f is defined between negative 2 pi and 2 pi, for which values of x is f of x less than 0. F of x less than 0. And don't think, every time I'm going to be given a graph like this, it's not going to always be this easy, but in some cases it is. So we can see, let me highlight the portions that are below 0. It's basically just the negative values of my function. So from here to here and here to here. So I would say, let me see exactly how they want that stated, just to make sure I'm staying consistent with how you'll see it in your answer key packets as well as the AP test. You'll say f of x is less than or equal to 0 when x is equal to, and there's one part that I forgot, because this is less than or equal to 0, I can't forget the starting point right here, so can't forget that guy. So it's when x is equal to negative 2 pi, negative 2 pi, or, so you can say or when there's multiple things that you need to work with, or it's between, so that took care of this part, now I got to take care of this part. Negative pi is less than or equal to x is less than or equal to 0, or take care of that part, and now I've got to take care of the last part, or it's between pi and 2 pi. Brackets here would also work. So solving inequalities is easy when we're given a graph, if it was only that simple, but it's not going to be the case always. For some inequalities, it's a little bit simple, but for some, we got to do the sign chart. Let's look at a couple simpler examples here. So an example here is, what are all the values of theta between, notice that's your domain restriction, when sine of theta is greater than or equal to square root of 2 over 2. So this is going to happen. So it's basically saying all the values that are greater than square root of 2 over 2. So I'm going to look at all the places where it's square root of 2 over 2. And because it's greater, it's going to be on the top half of the circle. That's why you end up with this line right here. It's greater than the square root of 2 over 2 right here. Because let's look at, for example, sine is the y values, right? So right here, for example, my y is equal to 1. 1 is greater than the square root of 2 over 2. And obviously, the square root of 3 over 2 is greater. So all of this portion right here. So the solution set would be, starting at the smallest side, pi over 4 is less than or equal to, because it's got an equal sign here. X is less than or equal to 3 pi over 4. And perhaps you might see it this way as well. But for AP purposes, you'll probably see this one more often than not. Second one here, let f of x equal that expression and g of x equal 3, and it wants all the values in the xy plane restricted, domain restriction, there's no plus 2 pi k or plus pi k, for which this is true, for which f of x is less than g of x. So I'm going to write 4 plus 2 cosine of x, that's my f of x, is less than my g of x, which is 3. And then I'm going to always solve it with my trig value on the left. Like I want to try to get my trig value on the left, so I'm going to keep it over here, minus, gives me 2 cosine. Theta is less than negative 1 divided by 2. And that's going to give me, when is, I forgot my x, when is cosine of x less than negative 1/2? Well, if I paste in my unit circle. Oh, probably not going to do it right here. There we go. Let me copy and paste the circle real quick. So if I paste in my circle, it's important that you always have a unit circle handy on these. So I'm trying to find when cosine is less than -1/2. When it's less than -1/2. So I'm going to look for -1/2 on the unit circle and circle it. It's right here. And less than means getting more negative. So here, a good way to check is the halfway points, like my pi over 2 is my 0, pi over 2, pi, and 3 pi over 2. I always check looking there. So my less than values are going to be here from 2 pi over 3 to 4 pi over 3, 2 pi over 3 to 4 pi over 3. Because a good litmus test is -1 is less than 1/2. And if I was trying to do it, do I do it the blue way here? No, because 1 is not less than 1/2. So 1 is not less than -1/2 rather. So I would say it's between 2 pi over 3. And because there is no, like in my function here, like in my original expression, there is no equal sign, so I don't put an equal sign here. So it's between 2 pi over 3 and 4 pi over 3. Now let h of x equal that, and this one equal that. So right here, remember, you're always going to try to get your cosine, like your sine and cosine on one side. So trig functions on left. Like, I'm always going to try to get my trig values on left. So let's write h of x first. H of x is 3 cosine x is greater than k of x, which is here, square root of 3 plus cosine of x. So this right here is just a weird looking constant, so I'm going to subtract cosine x on both sides. And because these have the same exponent, like this is just a singular cosine, this isn't cosine squared this time, or sine squared, I can subtract these. So 3 minus 1 cosine x is 2 cosine x is greater than square root of 3 over square root of 3 divided by 2. I'm looking for the places where cosine of x is greater than square root of 3 over 2. So once again on my unit circle here, I'm looking at the square root of 3 over 2. That happens here. Oh, I should circle that instead. Square root of 3 over 2. So, you kind of have to break this one apart because it's this portion right here. So it's only greater than the square root of 3 over 2 between here and here. And because 1 is greater than that. Square root of 3 over 2 is approximately like 0.87, I think, 0.866 if I'm not mistaken. So my greater portion is right here. But notice, because the unit circle is weird right here, I kind of need to break it into this blue portion here and a red portion here. Because if I tried to just go from here to here and here to here, this wouldn't make sense no matter how I ordered it. Because if I tried to say pi over 6, it's between pi over 6 and 11 pi over 6, I'd be talking about this part right here. If I tried to say 11 pi over 6 to pi over 6, then I've got, like if I try to write it this way, that doesn't make any sense because that's saying a bigger number is less than a smaller number. So I've got to break it into the blue portion. Let's do that. So the blue portion is 11 pi over 6 is greater than or equal to x is greater than or equal to 2 pi. Or my red portion here, I'm from 0 to pi over 6. So I have to break it up to take care of that part. So my red portion is here. My blue portion is here. For the last part, when we're solving inequalities, when we're finding if something is less than 0, greater than 0, and trying to do all the work that goes with that, I have to take the following steps. You can set f of x equal to 0 and solve. Okay, so let's do that. That's step 1. My f of x is my function is this. So this portion right here is my function f of x. So I'm going to say 2 sine squared theta plus sine theta equals 0. And notice that in this case, we may need a factor to solve. In this case, we do, because these both have a theta. These both have a sine theta. So I can factor out a sine theta equal parentheses 2 sine theta plus 1. So let's set this one. It's going to give me sine theta equals 0. And that happens when theta is equal to, and remember your domain restriction right here. It's my domain restriction. So my unit circle. Got my unit circle here, and I'm looking for when sine is equal to 0, so my y coordinate is 0. That happens here and here. So 0 and pi, so theta is 0 and pi. And then this one is going to solve that, set it equal to 0 and solve. It's going to give me sine of theta. I'm going to skip some steps, equals -1/2 minus the 1 and divide by 2. And that happens when my y coordinate is -1/2, which is here and here. So 7 pi over 6 and 11 pi over 6. So now it says in step 2 to create a sign chart with the solutions marked from step 1. And really, to create your sign chart, you got to go in order. So I'm going to have a sign chart here. Remember how to set this up. So my first value to test between is 0. And then I'm going to test next going around the circle between my options 0, pi, 7 pi over 6, and 11 pi over 6. The next one that I come to is pi, then 7 pi over 6, then 11 pi over 6. So I'm going to do them in that order. So what I need to do is go in and plug, like it says in step 3, test the value in one of the intervals by plugging it into the factored expression. My factored expression here is highlighted. Okay, factored expression is highlighted, and this takes a while. There's no way around it. It's usually easiest to pick a value on one of the axes if possible. So I'm just looking, and notice I don't have to check here. because that's before, like that highlighted portion will be before that, because my domain restriction, I have to end and start at 0 and end at 2 pi. So I also need to add in the end of my function here, so 2 pi. So really, if you wanted to make that prettier, you could erase this part and this part. So we're just going to test the values between that, because I'm between 0 and 2 pi. So a nice value to check between 0 and pi. 0 and pi would be pi over 2. I'm going to plug in pi over 2. And that's going to give me sine of pi over 2 so for this, let me move it down here. So sine of pi over 2, plugging it into my highlighted factored portion, times 2 sine pi over 2 plus 1. And notice here, that gives me sine of pi over 2 is 1. So 1 plus 2 times 1 plus 1, that gives me 3. So that's a positive here. Okay, and remember, you're checking positive and negative. And then I've got to check between pi over 6, pi, and negative pi over 6. So the thing is here, I'm going to have, let's see, the sine value here. The weird part is for this one, it's like, what do you plug in here? What do you plug in here? Not real sure here, because when I try to plug in on this one, there's no easy number to plug in. Well, to be able to do a sine chart on this one, this is kind of how I would approach it. So I'm going to look here, and let's say I have, I know not exactly what this value is. I don't know what this guy is. Like, we'll call that my question mark value. We know that the sine value is going to be between 0 and 1 half, right? 0 and 1 half. So maybe right here, we'll call our question mark that we plugged in for, the y value is 1/4, because between 0 and negative 1 half, there's going to be a 1/4. So first, we can say, on this, we can say sine of my question mark here plus times 2 times sine of my question mark plus 1 we don't know what the angle is, but we know what the output will be. We know that there's a 1/4 there, negative 1/4. And then that this will be 2 times negative 1/4 plus 1. That gives me negative 1/4 plus, that's negative 1 half plus 1. That gives me positive 1 half, which gives me negative 1/8. So right here, the most important thing is that I know that's negative. Then between 7 pi over 6 and 11 pi over 6, I'm just going to choose 3 pi over 2. Okay, and 3 pi over 2 is easy because that's a nice value. So I've got sine theta, and then times sine. We'll go ahead, instead of writing theta out, we'll just plug in 3 pi over 2. So sine of 3 pi over 2 and sine of 3 pi over 2. Sorry, I'm making this at the end of the day, a lot of mistakes here. Sine of 3 pi over 2, parentheses 2 sine 3 pi over 2 plus 1. That gives me negative 1 right here, times 2 times negative 1 plus 1. And that gives me negative 1 times negative 1. In parentheses, I'll have negative 1, so that's a positive 1. And then here, we'll say we have a value right here, kind of symmetrical to this. We know we got negative 1/4 for a y value right here again, like comma negative something comma negative 1/4. We're going to have a negative 1/4 y value here. So instead of plugging that back in again, why that's nice is I can just use, I'm going to know that this is going to be negative 1/8 again. This is going to be negative 1/8. So, because it's going to give me the same exact values again. So we can call this my star. So when I plug in for star, I get negative. So once again, I'm looking for where this happens on, where this happens and is less than 0. When is it less than 0? So when is it negative? Here and here. So we can say the theta is between pi and 7 pi over 6, or it's between 11 pi over 6 or 2 pi. So what I want you to do for this one, for example 6, try to solve that using the same steps I just did, but remember, when you factor out and do all your math here, you're going to have to slide and divide this one. You're going to have to slide and divide, or do AC method. Okay, go ahead, factor that out, and do your sign chart, and then check your answers on the answer key.